So for week 14, well, it's not really week 14, is it? This was supposed to be what we did at the beginning of this unit, and because I'm out of town, I wanted to move things around so that we could do optimization together before I left. So this is actually supposed to be our week 11 material, or 12. I think it was 12, but we're really doing it in week 13. So it has a slightly wrong date on it. But this is also because remember I told you my spring class, all of the sections got moved around due to an unforeseen circumstance. And so we'll just roll with it. So we've talked a little bit about some of these in relation to optimization, but let's talk about what some of these symbols mean. Again, remind ourselves that C of X is the cost of producing X units of the product. R of X is our revenue generated by selling X units of the product. And if you remember, my friends, that means that profit equals revenue minus cost. Marginal means that we're going to take a derivative because we're looking at the rate of change. So remember that means C prime of X is the marginal cost of producing X units of a product in dollars per item, and R prime of X is the marginal revenue generated by selling X units of the product in dollars per item. So for example 1, we said that let C of X be 20 plus X and plus 950. And that is our cost, our total cost in dollars of manufacturing X units of a certain commodity per day. What is the total cost if the production is set at 25 units per day? That is simply just finding C of 25. We're trying to figure out what our costs are at 25 units. So legitimately, all we have to do is just plug in 25 for X. So let's just find C of 25, which would be 20 times 25 plus 950. Or if we added all that up, it would be 1450. So $1,450. What instead is our marginal cost? Well, remember, marginal means take a derivative, so we are looking for C prime of X. So C is 20x plus 950, so our derivative, C prime, means the derivative of 20x is just 20, and the derivative of 950 is just 0, so it is simply $20 per item. We like when we get linear functions in this case. So if this is the case that our cost is changing at $20 per item, no matter how many items we've made, we have a constant changing. Our change is constant. It is always $20 per item. This means then what is the additional cost in dollars of raising the daily production level from 25 to 26 units per day? Well, that would be $20 per item or unit. I suppose I wrote item. We could also be unit. So $20 per unit times, well, we're only raising it by 1 unit, so it would just be an additional $20. So as a follow-up, let's interpret the cost and marginal cost function. So if C of X is the cost in dollars of manufacturing X superhero capes per day, let's interpret what C of 30 equals 7,500 and C prime of 30 equals 215. So C of 30 equaling $7,500 means the cost of producing, right? The cost of producing 30, like I think we were talking about superhero capes here, right? The cost of producing 30 superhero capes per day is $7,500. So not so bad. Now remember, what does marginal mean? What does our derivative mean? It means our rate of change. So C prime of 30 equaling $215 per cape, right? Superhero cape. No capes, right? As Edna Mode would say. So our cost is changing at $215 per cape. Our cost is increasing at $215 per cape. But it's only when X is 30. So it means that if we wanted to make one more superhero cape, our cost would go up by $215. So that one more would be the 31st. So we would say the cost to make one more cape will increase by $215. What this is going to say on the online homework is the cost of making, if we have 30 and we add one more, that is our 31st. So the cost of making the 31st superhero cape, right? 31st. The next one, superhero cape, is approximately, right? Approximately $215. So next we're going to talk about an instantaneous rate of change. Instantaneous just means take the derivative. That is all it means. So if I wanted to, and I have it here in a box, derivative is instantaneous rate of change, straight from the book. The derivative f prime of a measures the instantaneous rate of change of f of x at x equals a. F prime of a is instantaneous change. So if I have f of x equals 3x squared plus 2, and I want to find its instantaneous rate of change at x equals 2, I'm just looking for f prime of 2. So we are being asked for f prime of 2. So let's find f prime of x then. That's step 1, which would be 6x. Oh, that's it, 6x plus 0. So what is f prime of 2 then? Well, that would just be 6 times 2, which is 12. So our instantaneous rate of change here is simply 12. An analysis of the daily output of a shoe assembly line shows that about 60t plus t squared minus 1/9 t cubed units are produced after t hours of work, for t being between 0 and 8 hours. What is the rate of shoe production in units per hour when t is 3? One of the things I really like pointing out in this problem is that you are given a restricted domain for t, and that is between 0 and 8 hours. For those of you who haven't worked yet and or haven't gotten paid by the hour or had a job where you get time and a half or something along those lines, the reason why it's 0 to 8 is a standard work shift is 8 hours long. If a worker works past 8 hours, they are now in overtime. And oftentimes that's being paid at time and a half. So we would never, as business owners, allow our entire workforce to work overtime, which means that we wouldn't have the same level of production. Our level of production would go down after 8 hours because we're not going to allow all of our employees to keep working after 8 hours. So that's why we have that restriction that it's between 0 and 8 only, because that's just a normal 8-hour workday. So let's talk about what our rate of production is, shoe production here is when t is 3. So rate of shoe production, every time we see the word rate, we should immediately be assuming that we're talking about a derivative. So if we want to call our production, I'm just going to call our production P of t, okay? That means that P of t is equal to this 60t plus t squared minus 1/9 t cubed. And we're looking for P prime of t, which would just be 60 plus 2t, and then minus, well, that would be 1/9 times 3t squared. Or it's 60 plus 2t minus 1/3 t squared. And then what we really want is P prime of 3. So P prime of 3 then tells us that we have 60 plus 2 times 3 minus 1/3 times 3 squared, or 60 plus 6 minus 1/3 times 9, which is 3. So we end up with 60 plus 6 and minus 3. So we get 66 minus 3, or 63 units per hour. So during the normal 8-hour workday, our production line is increasing, right? Our rate of shoe production is 63 units per hour. We're increasing our production by 63 units per hour, right? When we're only 3 hours in. Okay. So we have some approximations of rates of change here, but I will say that we actually have removed this from the homework, and it's not covered in any of the homework or the quizzes or on the final. So we're going to skip this one, and it means we'll have to adjust a little bit the next example, okay? And since I'm traveling, I don't have the updated version of this file, which is at home on my computer and open at home in a different time zone. So sorry. So example 6 says, consider the function c of x equals 7x squared plus 16x plus 15 in thousands of dollars. So what is the marginal cost at the production level x equals 3? Well, we know marginal means take a derivative. So let's first find c prime of x. So c prime, well, we know at this point that that would be 7 times 2 is 14x, and then plus 16, and then we want to know c prime of 3. So c prime of 3 would be 14 times 3, which is 42. And then what we're going to do with that is add 16. So we end up with 58. But bear in mind what the units are in this section. And it says that this is in thousands of dollars, so it's actually $58,000 in this case is how fast our costs are changing. So C prime of 3 would be $58,000 per unit, right? And my secondary A is what we're going to skip. That was related to the one we just did, so don't worry about that. I also had it marked wrong on there. So let's look at B. If we let R be negative x squared plus 51x plus 40, and that's now our revenue in thousands of dollars generated by the production of X units, what is the break-even point? Well, hopefully we remember back to one of our first discussions about business applications, and that is what a break-even point is. The break-even point is when R of X equals C of X, or when your profit is 0. So in this case, R of X would be negative x squared plus 51x plus 40. And now we want to know where that one equals 7x squared plus 16x plus 15. So what we're going to do is we're just going to move all of the terms on the left over to the right. So we'll add an x squared, we'll subtract a 51x, and we'll subtract a 40. So we end up getting 0 equals, let's see, that would be 8x squared. 16 minus 51 is going to get us negative 35x. And then 15 minus 40 would be minus a 25. And then we are going to need to either use the quadratic formula or we're going to have to factor. And I was able to factor this one into x minus 5 and 8x plus 5 equaling 0. So that means x is equal to 5 or x is equal to a negative 5/8. And we can't have a negative number of units, nor would we end up having a fractional number of units. So this one doesn't fit. So we're looking at x equals 5 units as our break-even point. So at that point, our profit is nothing. So if we wanted to find our marginal revenue and our marginal cost at that point, it will help us make a decision on whether or not we should increase production. So remember, marginal cost is how fast at that point our costs are increasing or decreasing, and marginal revenue is how fast our revenue or money coming in is increasing or decreasing. So ideally, if we wanted to increase production, that would mean hopefully our costs are going down and our revenue is going up. If that's the case, ramp up the production, we're making more money because profit is revenue minus cost. If revenues are going higher and costs are going lower, that's ideal for profit. So let's see what happens when we look at that. Well, we can already find the marginal cost at our break-even point because we already know what our marginal cost function is. So we really want C prime of 5. So C prime of 5 will be 14 times 5 plus 16, or our marginal cost ends up being 86. So our costs are increasing at $86,000 per unit. That sounds like a lot of increase in the cost. Let's see what's happening with the revenue. So R prime of x then would be a negative 2x, right, plus 51. I'm not enthusiastic here because we got a negative on our slope here. So let's see. R prime of 5 gets me a negative 2 times 5 plus 51, or negative 10 plus 51. So we get a negative, or real positive, right? 41. So our R prime, our costs are increasing only at $41,000 per unit. So in this case, our costs are increasing at a rate that's more than double how fast our revenue is increasing. So if our costs are far outpacing our revenue, it would not be a good idea to continue production past this point. So we would say, since C prime of 5 is greater than R prime of 5, right? We do not increase production. So we do not want to increase production past x equals 5. Example 7 is kind of a fun one. This one is an application of, believe it or not, the product rule. So the width of a rectangle is increasing at a rate of 4 inches per second, and its length is increasing at a rate of 2 inches per second. At what rate is the area of the rectangle increasing when its width is 6 and its length is 9? So we have a rectangle, right? It has a length and it has a width. And here's the part that's hard to visualize sometimes, is that this rectangle is getting larger in both directions. It's getting bigger. It's changing. And we want to know, how fast is the area changing at this particular instance? So in this case, what we know is that area is equal to length times width. So we have to remember area equals length times width. But in this case, the length is changing in time and the width is changing in time, and so is the area. So this is actually an area in terms of time, and A of t is now an L of t times a W of t. So area is a function of length times a function of width, which means when we want to know how fast our area is changing, we're going to need to do a derivative and use the product rule. So it says, at what rate is the area increasing? So that is A prime of t. And so we would have to do L of t times W prime of t plus L prime of t times W of t. And this is where we have to now go figure out where those are in our problem. So let's see here. The width is increasing at a rate of 4 inches per second. So that is W prime. So that one we can plug in. So that one would be right here. This would be 4. Okay, let's see what else we can find. Length is increasing at a rate of 2 inches per second. That's L prime. Okay, so we can plug in L prime here, which is 2. And let's see what else we can find. What rate is it rectangle increasing when its width is 6? So that's W. So W is 6. Okay. And let's see here. That means we just need L. Oh, there it is. L is 9. So L is 9. So we're going to take L times W prime plus L prime times W. And when we put it all together, we get 36 plus 12, or 48. And remember, this is area in terms of time, so that would be inches squared per second. So we end up with our area changing at 48 inches squared per second. The last kind of application we're going to look at in terms of derivatives is in terms of physics. So something that we have to keep in mind is that properties of physics are actually related through derivatives and antiderivatives. So velocity is the derivative of position. So the way that I've always thought about this is we have position, which is s of t, not p of t, not h of t for height, or anything else. It is s of t. And then we take a derivative, right? We take a derivative in terms of time to get us to our velocity. Now, velocity, v of t, what does that mean? So position is where we are in terms of location. Velocity is how fast we're moving. So think about it, the speed of your car. Let's say you're driving. Your position is where you are along your path, your drive, your route to let's say school. Velocity is how fast you're driving, your speed of your car. And if I wanted to know how fast my speed is changing, my velocity, I'll take another derivative, and that's going to land me at acceleration, a of t. Acceleration is how fast or slow your velocity is changing. So this is when you push down the gas pedal. It's how hard you're pushing down the gas pedal. Or you're pushing down the brake pedal and you're slowing down. So how fast you're slowing down is your deceleration, which is just a negative acceleration. Now here's the other super cool part of this is if you were given an acceleration, you could take an integral in terms of time and find the velocity. And if you were given a velocity, you could take an integral in terms of time and find the position. We're going to get to that in the next week or so. But for now, we're going to focus specifically on derivatives involving physics. We'll come back to the antiderivatives when we get to our antiderivative applications. So let's see how one of these problems might look. A toy rocket is fired straight up into the air and it has a height s of t equals 160t minus 16t squared feet after t seconds. What is the rocket's initial velocity, which means initial means beginning. So what is its starting velocity? How fast is it going when it shoots off the ground? So that means we have to find first what the velocity is. How do we do that? We take a derivative. So let's do that. So v of t is the same as s prime of t, which means v of t is going to be the derivative of 160t minus 16t squared, which is 160, because remember this is in terms of t, 160 minus 32t. That's our velocity function. Now what is our initial velocity? Well, then now we want to find v of 0, which will be our 160 minus 32 times 0, or 160 feet per second. If you get to one of the problems in the homework that maybe has metric units, it's okay. It'll just be meters per second. Okay? So if you ever find one or you take a physics course and they do meters, it'll just have slightly different numbers. It won't be 16. In the front, it'll be a different number. Okay. What would then be our velocity after 2 seconds? Well, the nice thing is we already know what the velocity function is. So v of 2, we just have to plug it in. That means we get 160 minus 32 times 2, which is 160 minus 64, or 96 feet per second. Could we now find the acceleration? Well, remember, acceleration was the derivative of velocity. So a of t is going to be the derivative v prime of t. Oops. There we go. So what is the derivative of 160 minus 32t? Well, the 160's derivative is 0 because it's constant. So we just have our negative 32. And here's where I have to explain the units a little bit. Acceleration is in feet per seconds squared because it is a derivative of feet per second in terms of time. So you have another second in the denominator. There is only one acceleration, and that is the acceleration everywhere. And this is usually where I ask my students, when we do these problems, you're going to find out when we're talking about feet and seconds, your acceleration will always be 32, negative 32, when we're talking about what this is, which is projectile motion. And the question is why? Why would our acceleration be constant? Hopefully, it sparked in your brain something to do with gravity. This is the acceleration of an object due to the exertion of gravity. So gravity's force on the object is making it accelerate at negative 32 feet per second squared. So that's where this comes from. So every time we throw a rock or a ball, we drop something off of a building, something we fire a rocket, an arrow, something along those lines, its acceleration is always going to be negative 32 feet per second squared. And this is because we're ignoring air resistance and all those other things. These are kind of our ideal settings, we'll say. Okay. So could we figure out when our rock now hits the ground? And the answer is, well, sure. What is our height when our rocket hits the ground? Well, when it hits the ground, our height is 0 because it's at the ground. So literally all we're going to do is just take 0 and set it equal to our height, which is 160t minus 16t squared. And this one we can factor a 16t out and make it 10t minus t. So we end up with t equals 0 seconds, or I think I wrote the t, whoops. It's just 10 minus t, there we go. Or t equals 10 seconds. Well, it's not going to be 0 seconds because that's when we shot it off. So we shot it off from the ground, which is why it's 0 at t equals 0 seconds. So the one we're looking for is it returns to the ground after 10 seconds. And the last part of our problem asks us, how fast is it moving when it hits the ground? It's going to smash into the ground, and how fast is it going? You may be surprised by our result, but we'll find out. So if we look at v of 10 seconds, we're going to have 160 minus 32 times 10, which is 160 minus 320, which gives us a negative 160 feet per second. So it flew off the ground at a positive 160 feet per second, and after 10 seconds, it's smashing back into the ground at a negative 160 feet per second. So I'm hoping at some point some of you will take some physics classes and get to experiment with some of this projectile motion. So for those of you who haven't done this one already, this is homework 9. So go back and finish homework 9, and I will see you all on Tuesday.